What if everything you thought you knew about the darkest, most mysterious objects in the universe was, well, fundamentally incomplete? Imagine the most extreme light-eating vacuum.
Yeah.
Right? Something that just swallows everything whole and is, by definition, completely black.
The ultimate void.
Exactly. And now, imagine it glowing.
That sounds wrong. Like a paradox.
It totally sounds like a cosmic surprise, doesn't it?
Yeah.
You might think black holes are just cosmic vacuum cleaners, pulling everything into oblivion.
That's the standard picture, yeah.
But what if they're actually tiny, super efficient power stations? Or maybe even crucial clues to how our entire universe began and, how it works at its most fundamental level.
That's a much more interesting picture and much closer to what modern physics suggests.
Today, we're taking a deep dive into exactly that, this fascinating kind of mind-bending world of black holes, the very origin of our universe, and even the perplexing nature of time itself.
It's a big journey.
It is. We're going to try and unravel these mysteries, pulling insights from groundbreaking scientific theories. We're looking particularly at ideas explored by one of the greatest minds in science, drawing from sources like the theory of everything, black holes and cosmic origins, and its Hindi counterpart.
And our mission for you, our listener, is really to act as your guides through this cosmic landscape. We want to break down these, let's face it, really complex and often abstract ideas.
Yeah, they can be intimidating.
Totally. So we want to make them simple enough that, say, an 8th grader could get the gist of it. Our goal is to make these profound concepts understandable and hopefully reveal some surprising connections you might not have thought about before.
Right.
We'll explore what these sources tell us about the fundamental laws governing everything around us, from the tiniest particles to the biggest galaxies, and why these ideas aren't just theoretical curiosities, but actually crucial to understanding our own existence.
Okay, let's jump right in then. Let's unpack this. When we talk about black holes, the first thing that probably comes to mind is their inescapable gravitational pull.
The point of no return.
Exactly. But here's something interesting, historically speaking. Before the 1970s, even the top scientists didn't really have a precise, agreed-upon definition for the edge of a black hole.
That's right. It was a bit fuzzy.
Yeah. It was like everyone knew black holes were there, this region you couldn't escape from, but where exactly did there begin and the rest of the universe end? It wasn't clearly defined.
That's a great point. And the crucial concept that finally emerged to pin this down is called the event horizon.
Ah, the event horizon. Heard that term.
Yeah. Think of it as the ultimate point of no return. It's the spherical boundary, the surface, from which absolutely nothing, not even light itself, can escape to a large distance, to reach an observer far away.
Okay.
Once you cross that line, you are, for all intents and purposes, just inevitably pulled further into the black hole. There's no coming back out.
I can almost picture that. It's like maybe being in the middle of a really bustling, crowded Kumbh Mela.
Interesting analogy.
Once you step past a certain invisible line into the absolute densest part of the crowd, you just can't push your way back out to the open street. No matter how hard you try, you're just pulled further into the flow.
That Mela analogy actually works really well to ground it. Yes, that's exactly the feeling. The source we're looking at describes it similarly, like someone trying to run away from the police.
Oh, yeah.
Yeah, managing to stay one step ahead, right on the edge, but never truly getting clear away. You're always being pulled.
Wow.
And what's really fascinating here, maybe a bit counterintuitive, is how the light rays themselves behave right at this boundary.
Okay, how so?
Well, they don't approach each other like you might expect if they were all being sucked towards one central point.
Right, you'd think they'd converge.
You would. But instead, they either stay perfectly parallel to one another, basically tracing out the exact surface of the event horizon, or they actually move away from each other.
Away? That's weird.
It is. Because think about it. If they were to approach each other and eventually cross paths, that would imply they were already falling inward.
So they wouldn't be on the boundary anymore.
Exactly. They would have already crossed it and fallen in. So the ones precisely on the boundary have to stay parallel or move apart.
So it's not like beams converging, but more like perfectly straight lines, or even spreading out. That almost sounds orderly for such a chaotic object as a black hole.
It is, in a strange mathematical way. Another way to visualize it is like the edge of a shadow cast by the sun.
Okay.
The light rays that form the very edge of that shadow don't converge, do they? They run parallel.
I see.
That's how the event horizon works. It's the precise edge of where light can just manage to hover or escape. And anything beyond it is in the shadow of inevitable gravitational capture.
Got it. And this precise definition you said around the early 1970s, that must have been a huge step forward.
Oh, absolutely. It gave physicists a solid mathematical framework to really start analyzing black hole behavior.
Okay, here's where, for me, it gets really interesting. Imagine a fundamental rule in the universe where some quantity, can only ever stay the same size or get bigger. It can never, ever shrink.
Like a cosmic one-way street for size.
Exactly. And this is precisely what was discovered about the area of a black hole's event horizon, a property that apparently deeply surprised the scientists working on it.
That's a great way to put it. This non-decreasing property of the event horizon's area was a profound revelation back then. It states quite simply that the surface area of a black hole's event horizon can only increase or stay constant over time.
So it never decreases.
Never. This happens whenever matter or radiation falls into the black hole. Anything goes in, the area gets bigger, or at worst, stays the same. It can never get smaller.
So if a star gets swallowed, the black hole gains mass, obviously, and its event horizon expands to match. That sounds almost too neat. Like, was this immediately accepted? Such a profound rule.
Well, the calculations were compelling. If any mass or energy crosses that horizon, the surface area must increase. And it gets even more dramatic when you think about black hole collision.
Oh, right, when two black holes merge.
Exactly. If two black holes collide and merge to form a single larger black hole, the area of the new black hole's event horizon is always greater than the sum of the areas of the two original black holes.
So it's not just adding them up, it's more than the sum.
Yes. It's a fundamental constraint ensuring the resulting black hole always has a larger event horizon area than its two parents combined. This was a really unexpected restriction on their behavior, and the source mentions the scientist who first calculated this was apparently so excited with my discovery that I did not get much sleep that night.
I bet. That's a real eureka moment, finding a rule like that governing these monsters.
Absolutely. It felt like uncovering a deep truth, suggesting a connection to maybe other fundamental laws of physics.
That's incredible. And what's even more fascinating, I think, is how this area increase, which sounds so specific to black holes, right? How it then connected to something much more universal, something called entropy. It really does feel like the universe was sort of whispering hints there.
The connection is definitely profound. This non-decreasing behavior of a black hole's area, it strongly reminded physicists of the behavior of entropy.
Okay, so entropy, remind us quickly what that is.
Sure. Entropy is a fundamental concept in physics. Basically, it measures the degree of disorder or randomness in a system.
Right.
And it's a matter of common experience, really, that if you just leave things to themselves, disorder tends to increase. Things get messier over time, not neater.
Oh, I know this one. It's like a neatly packed lunchbox in the morning versus how it looks after a school day.
Chuckles, yeah.
All messy, food mixed up, maybe spilled a bit. Or think about a pile of neatly folded Saris versus a pile that someone's rummaged through looking for the right one.
Perfect examples.
Disorder just naturally increases if you leave things alone, right? Like a house without repairs, it gets messier.
Precisely. Your everyday experience illustrates it perfectly. The second law of thermodynamics, which is a cornerstone of physics, explicitly states this. The total entropy, or disorder, in a closed system always tends to increase over time.
Okay.
So Jacob Buchenstein, who was a brilliant research student at Princeton at the time, he proposed something radical. He suggested that the area of the event horizon was actually a measure of a black hole's entropy.
Wow. So the black hole's surface area is its disorder.
In a sense, yes. Or at least proportional to it. This suggestion was revolutionary because it kind of saved the second law of thermodynamics when things fall into a black hole.
How so?
Well, if matter, which has its own entropy, falls into a black hole and disappears from view, you might think the total entropy of the universe has decreased, violating the second law.
I see the problem.
But if the black hole's area increases when stuff falls in, and if area is entropy, then the black hole's entropy goes up, potentially compensating for the lost entropy of the matter that fell in.
Okay, so Bekenstein's idea sounds really elegant. It connects black holes to this fundamental law of entropy. Was that the end of the story? Or did it actually open up, like, new puzzles?
It definitely opened up a big one.
Because...
Right.
Wait, if a black hole has entropy, it must have a temperature, right? Don't those two always go together in physics?
Exactly. That's the connection. If something has entropy, it must have a temperature.
And if it has a temperature, it must emit radiation, like anything hot.
Yes. Anything with a temperature above absolute zero has to radiate energy.
But black holes, by their very definition, aren't supposed to emit anything. They swallow light. That sounds like a fatal contradiction.
You've hit on the fatal flaw perfectly. That was the exact term used. It was a huge contradiction at the time, and it made many scientists, including the famous one whose work we're mainly exploring today, very skeptical of Bekenstein's idea initially.
I can see why. It's like, imagine heating up a tava, a griddle, on the stove, glows red, emits heat. Even things that aren't red-hot, cooler things, they still emit radiation, just maybe infrared, less noticeably.
Right. All objects radiate based on their temperature.
So if black holes had a temperature, they had to emit, which seemed to go against their very nature as perfect absorbers. How could something that absorbs everything also radiate? That paradox seems huge.
It was a significant hurdle, absolutely. It seemed like you had to choose. Either Bekenstein was wrong about entropy, or our fundamental understanding of black holes and thermodynamics was flawed.
Okay, so how did we get past this fatal flaw? Wait, how can something defined as absorbing everything, including light, actually emit? My mind is kind of buzzing with intrigue here. What kind of mechanism could possibly explain that?
This is where quantum mechanics makes a truly astonishing entrance. It leads to one of the most unexpected and profound breakthroughs in modern physics. The prediction that black holes do, in fact, emit particles and radiation. Yes. This phenomenon is now famously known as Hawking radiation.
Ah, okay.
And it was a massive surprise to the scientific community at the time, but it directly resolved Bekenstein's fatal flaw.
So how does this work? What's the secret behind a black hole actually glowing? It sounds like magic.
It's definitely mind-bending, but the mechanism can be explained relatively simply, surprisingly, thanks to the strange rules of quantum mechanics.
Okay, I'm ready. Lay it on me.
Right. So what we normally think of as empty space isn't actually empty at all.
Uh-oh.
Due to the quantum mechanical uncertainty principle, which basically says you can't perfectly know certain pairs of properties, like a particle's exact position and momentum, at the same time, things are always a bit fuzzy.
Right, the uncertainty principle.
And one consequence is that pairs of virtual particles and antiparticles are constantly popping into existence out of the vacuum.
Just appearing from nowhere.
Essentially, yeah, for incredibly brief moments. Then they almost immediately annihilate each other, vanishing as quickly as they appeared. Normally, this happens so fast we don't notice, and energy is conserved over any measurable time. They're like fleeting, ghostly presences.
Okay, ghostly particles popping in and out. Got it.
Now, imagine this happening right near the edge of a black hole's event horizon, where gravity is incredibly intense.
Okay. Like our Delhi metro station analogy from before. Imagine during rush hour, these tiny pairs of people pop up, one with a positive energy ticket, one with a negative energy ticket. Normally, they find each other instantly, cancel their tickets, and vanish back into the crowd.
That's a fantastic analogy. It works perfectly. Now, here's the twist near the black hole. its gravity is so strong that if a virtual antiparticle pair pops into existence right there, the black hole can actually pull one of the partners in before it has a chance to annihilate its partner.
It separates them.
It separates them. Specifically, it tends to pull in the partner with negative energy relative to the black hole's gravitational field.
Negative energy. That sounds weird, too.
It is weird, but it's allowed in quantum field theory near strong gravity. Because this particle now has negative energy as it falls into the black hole, it effectively reduces the black hole's total mass energy. Crucially, it no longer needs to annihilate its partner outside.
So the other one is left stranded.
Exactly. The positive energy partner, left alone just outside the event horizon, has nowhere to go but escape out to infinity. It becomes a real particle.
Wow.
And to us, observing from far away, what does this look like? It looks like the black hole itself has just emitted that particle.
That is just incredible. So the black hole isn't technically emitting from inside, but it's causing particles to be created at its edge and then flung outward.
That's the essence of it. And because the negative energy particle fell in, the black hole actually loses a tiny bit of mass in the process.
So these black holes are, in a sense, sort of boiling off, slowly shrinking as they lose energy through this radiation.
That's exactly right. They evaporate extremely slowly for large ones, but they do evaporate. It's like the universe's ultimate recycling program for mass and energy-taking matter that falls in and eventually turning it back into radiation.
Mind blown. And the source mentions this radiation is like heat from a hot body, right? With the temperature that depends only on the black hole's mass.
Correct. And counterintuitively, the higher the mass of the black hole, the lower its temperature and the slower it radiates.
So bigger black holes are colder.
Much colder. A black hole with a mass just a few times of our sun would have an incredibly tiny temperature, only about 1/10,000,000th of a degree above absolute zero.
That's unbelievably cold. Colder than deep space.
Way colder. The universe's background microwave radiation, the leftover heat from the Big Bang, is about 2.7 degrees above absolute zero. So these big solar mass black holes are actually absorbing more energy from the background radiation right now than they're emitting through Hawking radiation.
Okay, so they'll actually grow for the time being.
For an incredibly long time, yes. They would take something like 10 to the power of 66 years to evaporate completely. That's vastly longer than the current age of the universe.
Right, 10 followed by 66 zeros.
Right.
Okay, that's a long time. So we're not actually seeing these giant glowing black holes then. It's a bit of a letdown after that amazing explanation.
Not the supermassive ones, no. The radiation is far too faint and low energy for us to detect directly against the cosmic background. But here's where it gets exciting again. There's a theoretical possibility of much smaller black holes. They're called primordial black holes.
Primordial, meaning from the beginning.
Exactly. These are hypothetical black holes that wouldn't have formed from collapsing stars like the big ones do. Instead, they could have formed in the very, very early universe. From the direct collapse of tiny, dense regions in the incredibly hot, high-pressure plasma soup that existed just moments after the Big Bang. If there were slight irregularities, some spots much denser than others, they could have collapsed under their own gravity right then and there.
And these would be much smaller.
Potentially much, much smaller. And because their temperature is inversely proportional to their mass,
they would be much hotter.
Exactly. They could be incredibly hot and emit radiation at a much, much greater rate.
Oh, like the example in the source. A primordial black hole with the mass of a mountain, but compressed down to the size of an atom's nucleus.
Yes. That kind of object wouldn't be black at all.
It would be white hot.
White hot, yes. And according to the calculations, it could actually be radiating energy at a rate equivalent to 10 large power stations, something like 10,000 megawatts.
Wow. A tiny black hole is a power source. That's mind-blowing.
It is. These things would be furiously emitting high-energy particles, X-rays, and gamma rays.
So could we detect those?
Well, that's the hope, but it's incredibly difficult. They'd be tiny, maybe scattered throughout the universe, very far away.
So what are we looking for?
We'd primarily be looking for bursts of gamma rays with very specific energy characteristics, unlike gamma rays from other astronomical sources. One detection method involves looking for faint flashes of light in the upper atmosphere called Cherenkov radiation.
Cherenkov radiation.
Yeah, it's basically like a tiny sonic boom, but for light. When a super high energy particle, like one emitted from an evaporating primordial black hole, hits the atmosphere faster than light travels in the air.
Right, light slows down in air.
Exactly. It creates this faint cone of blue light. It's the same effect you see giving nuclear reactors that eerie blue glow underwater.
I've seen pictures of that.
So we have detectors looking for these flashes, but lots of things cause flashes. To be sure it's maybe a primordial black hole, you'd need to see the same flash simultaneously from 2 or more detectors located far apart. That helps rule out things like lightning or just a single cosmic ray hitting the atmosphere nearby.
Got it. So the search is ongoing for these mini glowing black holes. And even if we don't find them, a negative search actually tells us something profound, right? It's not just a failure.
Absolutely. It's a scientific insight either way. If we don't find any evidence for primordial black holes, or at least constrain how many there could be,
Yeah.
it gives us vital information about the conditions in the very early universe. It suggests the early universe must have been incredibly smooth and uniform, with very high pressure that resisted collapse. If it had been really chaotic or lumpy with big density fluctuations...
We expect lots of these things to have formed.
Precisely. So a null result still tells us something crucial about those first moments after the Big Bang. It helps refine our models of cosmic origins.
That's quite a revelation in itself. And this whole discovery of Hawking radiation, it sounds like it must have completely upended what scientists thought they knew about black holes. How was it received? Especially since, as you said, it seemed to bring together these 2 giants of 20th century physics. General relativity for gravity and quantum mechanics for the very small.
It certainly ruffled a lot of feathers initially. When the results were first presented, there was immense skepticism. People really struggled with the core idea that a black hole, the ultimate absorber, could emit anything, let alone sort of boil off into radiation. It seemed deeply paradoxical.
Yeah.
But eventually, after the calculations were rigorously checked, rechecked, and confirmed by others, the scientific community largely came to accept it. They realized that if our understanding of both general relativity and quantum mechanics is fundamentally correct, then black holes must radiate. There was no escaping the logic.
And it was a huge step because it united these 2 theories.
Exactly. This prediction was truly monumental because it was the first concrete, potentially testable prediction that relied crucially on both general relativity and quantum mechanics working together. Previously, they'd mostly lived in separate domains. This hinted strongly at the possibility of a deeper, more unified theory of physics still waiting to be discovered.
And it also changed the view of black holes being like the ultimate endpoints, right?
Yes. It suggested that gravitational collapse isn't quite as final and irreversible as classical physics implied. If an astronaut, unfortunately, falls into a black hole...
Yeah, poor astronaut.
Their mass and energy are incorporated into the black hole, yes. But eventually, over an incredibly long time scale, that equivalent mass energy will be returned to the universe in the form of Hawking radiation.
So the astronaut gets recycled in a way. Though I imagine their personal concept of time would definitely come to an abrupt end as they were, well, crushed out of existence.
Indeed. Their mass and energy would be conserved and eventually re-emitted, but certainly not their structure or identity. What's really crucial here, though, is that Hawking radiation was the first strong indication from theoretical physics that quantum mechanics might actually be able to resolve the problem of singularities.
Those points of infinite density where the physics breaks down.
Exactly. The singularities predicted to exist inside black holes by classical general relativity, and critically, the singularity predicted at the very beginning of the Big Bang itself.
Right.
If quantum effects can make black holes evaporate, and perhaps prevent a true singularity from forming inside them, maybe quantum effects could also describe the universe's origin without needing an initial singularity where everything breaks down. It opened a whole new avenue for thinking about the universe's beginnings.
Okay, so we've talked about these incredible cosmic vacuum cleaners that actually kind of glow objects that maybe recycle the universe's matter over unimaginable timescales. But now let's pivot to an even grander mystery. The very beginning of everything.
Right.
Our universe itself. How did it all kick off? From, well, maybe not nothing, but from something incredibly small and hot to everything we see today, including us.
This brings us squarely to the hot Big Bang model, which is really the standard, generally accepted scientific story of our universe's history.
Okay.
It posits that our universe began from an incredibly hot, incredibly dense state, maybe even zero size, though quantum gravity might smooth that out, as we just discussed, but certainly a state of unimaginably high density and temperature. And then it expanded and cooled over billions of years to become the vast, complex cosmos we observe today.
I can kind of imagine our universe as like an enormous pressure cooker, maybe, or even one of those big idolized steamers.
Okay, I like the pressure cooker idea. Go on.
It starts unbelievably hot and tiny, filled with this dense, energetic steam, right?
Yeah.
And as it expands, the steam inside, which is like the particles in the early universe, cools down. And as it cools, things can start to condense and form.
That's a great way to visualize the expansion and cooling process. It captures the essence really well. In the very first second after this initial moment, the universe's temperature would have been around 10,000 million degrees Celsius.
Wow, okay, that's hot.
Unimaginably hot. At that temperature, it was just this rapidly expanding, intensely hot soup of fundamental particles. Photons, light particles, electrons, neutrinos, their antiparticles, and roughly equal numbers of protons and neutrons bouncing around like crazy.
Just a particle soup.
Pretty much. But as it continued to expand and cool, which happened incredibly rapidly in the beginning, different things started to happen. Particles formed, and then elements began to form. For instance, when the temperature dropped to about 1 billion degrees.
So pretty hot.
Still incredibly hot, yes, but cool enough after about 3 minutes for protons and neutrons to slow down enough to stick together when they collided. They formed the nuclei of the lightest elements, mostly deuterium, that's heavy hydrogen, and then helium.
And the amazing thing is, the amount of helium and deuterium predicted by these Big Bang calculations, it perfectly matches the amounts we actually observe in the universe today, right?
Yeah.
It's like finding the universe's chemical fingerprint from its birth.
Absolutely spot on. This precise prediction and the subsequent matching observation known as Big Bang nucleosynthesis is one of the strongest pillars of evidence supporting the hot Big Bang model. It's incredibly compelling.
And there's another huge piece of evidence, isn't there? Something about background radiation.
Yes, perhaps the most compelling evidence of all. The cosmic microwave background, or CMB.
The CMB.
Right. This is this faint, almost perfectly uniform glow of microwave radiation that permeates the entire universe. It's everywhere we look. And it's now cooled down due to the universe's expansion to just a few degrees above absolute zero specifically, about 2.7 Kelvin.
So what is it? Where did it come from?
It's essentially the afterglow of the early hot universe. It's the leftover light from a time about 380,000 years after the Big Bang, when the universe had cooled down enough for electrons and protons to combine and form neutral atoms.
And why was that important?
Because before that, the universe was an opaque plasma. Photons kept scattering off free electrons like light in a dense fog. But once neutral atoms formed, the photons could suddenly travel freely through space without constantly bumping into electrons.
The universe became transparent.
Exactly. And the CMB is the light from that exact moment, stretched out by cosmic expansion over billions of years into the microwave range we detect today. It was accidentally discovered by Penzias and Wilson in 1965.
Right, they were working on satellite communication, wasn't it?
They were. And they kept detecting this persistent background noise they couldn't get rid of. Turns out they'd stumbled upon the echo of the Big Bang itself. It was definitive observational proof that our universe started from a hot, dense state. You can think of the CMB map as the cosmic baby picture of our universe.
A baby picture. I like that. Okay, so we have this hot soup. It cools, elements form, light breaks free. But how did all this generally smooth, cooling gas turn into the actual stars and galaxies we see today, that still seems like a huge leap from a uniformish cloud to these magnificent, complex structures. What was the driving force?
It's a slow, patient dance directed primarily by gravity, playing out over billions of years, even though the universe was incredibly smooth on large scales, as shown by that very uniform CMB.
Yeah.
It wasn't perfectly smooth. There must have been tiny, minuscule variations in density from place to place. Little quantum fluctuations maybe left over from the very beginning and stretched out by inflation. Some regions were just ever so slightly denser than others.
Just tiny differences.
Infinitesimally small initially. But in these slightly denser regions, the extra gravitational attraction, however weak, began to pull in more matter from the surroundings. This caused the local expansion in those denser spots to slow down a bit compared to the less dense areas around them.
So gravity acted like an architect, slowly starting to gather the building blocks from this cosmic dust, amplifying those tiny initial seeds.
Exactly. It's a testament to the relentless cumulative power of gravity over vast cosmic timescales. And as these regions began to contract under their own gravity, another effect came into play: rotation.
They started spinning. Why?
Well, the gravitational pull from matter outside these collapsing regions, maybe slightly off-center, could exert a tiny twisting force, a torque. Also, the initial gas cloud itself might have had some slight inherent rotation. As the cloud collapsed and got smaller.
It would spin faster, like the dancer pulling their arms in.
Precisely. Like a Kathak performer or an ice skater, pulling their arms in close to their body. As a collapsing gas cloud shrinks, it has to spin faster to conserve angular momentum. Eventually, when these collapsing regions became small enough, they would be spinning fast enough that the outward centrifugal force would balance the inward pull of gravity, at least in the plane of rotation. This naturally formed those beautiful, flattened, rotating, disc-like structures we call galaxies, like our own Milky Way.
Wow, so gravity pulls it together, and the spin flattens it out into a galaxy. And then, presumably, within those brand new galaxies, the stars themselves started to form.
Yes. The process kind of repeats on smaller scales. The gas within these newly formed galaxies wasn't perfectly uniform either. It would continue to clump together due to gravity, breaking up into smaller clouds or nebulae.
More collapsing
clouds. And these smaller clouds would collapse further under their own self-gravity. As they collapse, the gas particles inside collide more and more frequently, causing the gas to heat up dramatically.
Gravity compressing it heats it up.
Exactly. Eventually, the temperature and pressure in the very core of these collapsing clouds would become absolutely immense, reaching millions, even tens of millions of degrees Celsius.
And that's the ignition point.
That's the ignition point. At those temperatures and pressures, nuclear fusion reactions ignite. Primarily, hydrogen nuclei, protons, start fusing together to form helium nuclei, releasing a tremendous amount of energy in the process.
Like a controlled hydrogen bomb.
In essence, yes, but sustained over billions of years. This outflow of energy creates outward pressure that finally balances the inward pull of gravity, stabilizing the collapsing cloud. And that's how a star, like our sun, is born. It starts shining, radiating immense energy as heat and light, powered by these nuclear reactions in its core.
Amazing. But wait, what about the heavier elements? The carbon, oxygen, iron, the stuff that makes up planets like Earth and even us. Where did those come from if the Big Bang basically only made hydrogen and helium?
That's where the story gets even more dramatic and beautiful. Those heavier elements come from the life and, more importantly, the death of massive stars. It's a truly magnificent cosmic recycling program.
Recycling? How?
So, stars more massive than our sun burn through their hydrogen fuel much, much faster. They have to be much hotter in their cores to generate enough outward pressure to counteract their stronger gravity.
Okay, bigger stars live fast, die young.
Pretty much. Once they exhaust the hydrogen in their core, they start fusing helium into heavier elements like carbon and oxygen. And if they're massive enough, they continue this process, fusing carbon into neon, neon into magnesium, then silicon, and eventually building up a core of iron.
Iron. Is that the end of the line?
For fusion energy, yes. Fusing iron actually consumes energy rather than releasing it. So once a massive star builds up an iron core, it faces an energy crisis. There's no more nuclear fuel to burn to hold itself up against its own immense gravity.
So what happens?
The core collapses catastrophically in a fraction of a second. It can bounce back, sometimes forming an incredibly dense neutron star, or if it's massive enough, collapsing all the way into a black hole. At the same time, the outer layers of the star are blown off in a tremendous violent explosion called a supernova.
Supernova.
Yeah.
The big ones.
The really big ones. For a short time, a single supernova can outshine its entire host galaxy, becoming one of the brightest objects in the universe. There are unbelievably powerful events.
And these explosions are what spread the heavy elements.
Precisely. They are the universe's ultimate element factories and distribution centers. Not only do they create even heavier elements during the intense heat and pressure of the explosion itself, elements heavier than iron, like gold and uranium, but they also violently fling all the elements the star produced during its lifetime, the carbon, oxygen, silicon, iron, everything, back out into the interstellar gas clouds of the galaxy.
Wow. So they seed the next generation.
Exactly. This enriched gas, now containing these heavier elements, mixes with the existing hydrogen and helium and becomes the raw material for the next generation of stars and planets. Our own sun, for example, is considered a second or third generation star.
How do we know that?
Because we can measure its composition, and it contains about 2% of these heavier elements. That might not sound like much, but it's far more than was created in the Big Bang. That 2% is the cosmic debris, the ashes, from earlier generations of massive stars that lived, died, and exploded billions of years ago.
And our Earth, the planets, us, we formed from that same debris.
Absolutely. It's from this recycled material, this cosmic stardust enriched by countless supernovae, that our Earth and the other planets in our solar system ultimately formed. So when Carl Sagan famously said, "We are made of star stuff," he wasn't being poetic.
He was being literal.
He was being completely literal. We are, quite fundamentally, made from the ashes of ancient giant stars. It's a truly profound connection we have to the cosmos and its history.
Okay, the Big Bang model, with stars forging elements and galaxies forming, it explains so much about our universe. But like you hinted earlier, and like any really good mystery, it seems it left some pretty big questions unanswered. Some crucial pieces of the puzzle that classical physics, even general relativity, couldn't quite resolve on its own.
That's right. Despite its incredible successes, the standard hot Big Bang model, especially before the refinements we'll discuss, had some significant lingering questions, some real head-scratchers for cosmologists.
What were the main ones?
The sources highlight 4 major ones. First, why was the early universe so incredibly hot to begin with? The model starts from that hot, dense state, but it doesn't really explain the origin of that initial heat.
Okay, it assumes the heat.
It assumes the heat, yeah. Second, why is the universe so remarkably uniform on a large scale? When we look out at the cosmic microwave background, the temperature is almost exactly the same in all directions, to within tiny fractions of a degree. But according to the standard model, regions on opposite sides of the sky were too far apart in the early universe to have ever exchanged heat or information. So how did they know to be at the same temperature? This is called the horizon problem.
The horizon problem. Okay, how could opposite sides coordinate? Got it. What else?
Third, why did the universe start expanding at just the right speed? It seems incredibly fine-tuned. If it had expanded just a tiny bit slower, gravity would have pulled everything back together in a big crunch long ago. If it had expanded just a tiny bit faster, galaxies and stars would never have had time to form. The universe would have become too dilute too quickly. This is known as the flatness problem, because this critical expansion rate corresponds to a spatially flat universe.
Flatness problem. Like balancing on a knife edge.
Yeah, and the fourth?
The fourth is what caused the small density fluctuations in the first place, the ones that eventually grew into all the stars and galaxies we see today. The Big Bang model needed these initial seeds for structure formation, but it didn't explain where they came from. Were they just put there randomly as initial conditions?
Okay, so initial heat, large-scale uniformity, horizon problem, the perfect expansion rate, flatness problem, and the origin of cosmic structure. Those sound like pretty fundamental questions. They really are. And these are questions that classical general relativity on its own struggled to answer, especially because, as we mentioned, it predicted that inescapable singularity at the very beginning of time.
Right, the point where the physics breaks down.
Exactly. Classical general relativity predicts the state of infinite density and temperature at time zero, where all the known laws of physics simply stop making sense. This means the theory literally cannot describe its own beginning. It hits a wall.
So it can't explain the initial conditions.
Precisely. If the universe really started at such a singularity, it would have a definite boundary in time, a beginning point. But why should it have started in just such a specific way to lead to the remarkably uniform, flat, structured universe we observe today? It feels like an incredibly fine-tuned, almost miraculously preordained initial condition, which scientific theories ideally try to avoid. We prefer explanations that arise naturally from the laws themselves.
This raises a really fascinating thought, and maybe a slightly philosophical one. Is our universe just perfectly tuned for life? Or is there something else going on that just makes it seem that way to us? It almost feels too convenient that all these conditions, the expansion rate, the uniformity, the laws of physics, are just right for us to be here asking these questions.
This leads us directly into the territory of the anthropic principle. It's a rather profound and sometimes quite controversial idea in physics and cosmology.
Anthropic principle. Okay, what does it suggest?
In its simplest form, it suggests that we observe the universe the way we do because we exist, or more precisely, because we exist in a region of space-time suitable for the development of intelligent life.
How does that help explain things?
Well, the idea is, if other regions of the universe, or perhaps even other hypothetical universes, had different laws or conditions, say an expansion rate that was too fast, or fundamental forces that didn't allow stable atoms or stars to form, then there would simply be no observers like us in those regions to notice.
Okay. So we only see the kind of universe where observers can exist.
Exactly. We inevitably find ourselves in a universe, or a part of the universe, that has the properties necessary for our own existence. So the apparent fine-tuning isn't necessarily a miracle. It might just be a selection effect. We couldn't observe it any other way.
So it's kind of like finding a really comfortable seat on a crowded Indian Railways train.
Okay, another train analogy. Let's hear it.
You might sit there and wonder, wow, how did I get such a perfect seat? Window view, enough legroom, not too crowded. You might marvel at your luck, but you wouldn't really notice or contemplate the thousands of other uncomfortable, cramped, or otherwise unsuitable spots in all the other coaches because you're simply not sitting in them.
That's a very intuitive way to put it. You're observing the universe from your privileged, life-supporting location, and perhaps drawing conclusions based on that selected sample. And the hot Big Bang model, especially before the concept of inflation, really struggled with that uniformity problem we mentioned, the horizon problem. There just wasn't enough time in the standard model for heat to flow between distant regions and even out the temperature across the entire observable universe. Yet, the CMB shows us it is incredibly uniform.
So it looked like those regions must have started out at exactly the same temperature, somehow coordinated across vast distances that couldn't communicate.
Exactly. Without a physical mechanism to explain this coordination, it seemed almost like a miraculously chosen initial state for the universe, or that the universe began in an impossibly ordered low-entropy state. The anthropic principle offered a kind of philosophical way out by saying, well, we're here observing a uniform universe, so it must have been uniform enough for us to evolve.
But that doesn't feel entirely satisfying as a scientific explanation, does it? It explains why we observe it that way, but not how it got that way physically.
Precisely. Scientists generally prefer explanations that provide a physical mechanism, a dynamic process that leads naturally to the observed state, rather than just appealing to our own existence as the reason, and that's where inflation comes in.
Okay, so how do we explain this incredible uniformity and the seeming fine-tuning of the expansion rate without just resorting to saying, well, we're here, so it had to be this way? What's the physical mechanism?
This is where Alan Gough's inflationary model, proposed back at MIT in the early 1980s, offered a truly revolutionary physical solution to those nagging Big Bang problems, the horizon, flatness, and even the structure problems.
Inflation. Okay, what's the core idea?
The core idea is that in the very, very early universe, we're talking within the first tiny, tiny fraction of a second, like 1035 seconds or something unimaginably small.
Wow. Okay, really early.
There was a period of extremely rapid exponential expansion. The universe didn't just expand, it briefly ballooned outwards at an absolutely astounding rate, doubling in size many, many times over in that minuscule instant, far, far faster than the more leisurely expansion we see today.
Exponential expansion. That sounds dramatic. Like getting an unbelievably massive, sudden Diwali bonus, maybe?
Chuckles, a Diwali bonus for the universe. Explain.
Well, imagine your bank account suddenly, for just a tiny fraction of a second, swells exponentially by an enormous factor. It would instantly smooth out all your previous little financial ups and downs, wouldn't it? Everything would look flat and huge afterwards before settling down to more normal, slower growth.
That's actually a brilliant analogy. It captures the smoothing effect perfectly. Or another common one is blowing up a balloon.
Yeah, the balloon.
As you inflate a balloon rapidly, any wrinkles or bumps on its surface get stretched out and become almost imperceptible, right? The surface looks much flatter and smoother when it's huge compared to when it was small and wrinkled.
Right. Makes sense.
So this incredibly rapid inflationary expansion would have taken any tiny, potentially irregular patch of the very early universe and stretched it out enormously, making it far, far larger than the entire observable universe we can see today.
So that's how it solved the uniformity problem. It just stretched everything out flat and smooth.
Exactly. Any initial irregularities or temperature differences would be smoothed out by this immense stretching, explaining why the universe looks so incredibly uniform on large scales today. The different regions we see were actually incredibly close together before inflation blew them far apart.
And the flatness problem, the expansion rate being just right.
Inflation solves that too, naturally. Just like blowing up the balloon makes its surface appear flatter, this exponential expansion would have driven the geometry of space itself towards being incredibly flat, automatically tuning the expansion rate to that critical value we observe.
Wow. Okay, that's elegant. And what about the seeds for galaxies, the density fluctuations?
Inflation handles that beautifully as well. Remember those tiny quantum fluctuations, the virtual particles popping in and out of existence due to the uncertainty principle?
Yeah, the quantum jitters.
During inflation, these minuscule quantum jitters would have been stretched along with everything else. Stretched from microscopic quantum scales up to macroscopic astronomical scales.
So inflation amplified the quantum weirdness.
It amplified the quantum weirdness, yes, creating slight variations in density across the vastly expanded space. These amplified fluctuations became the primordial seeds, the slightly denser regions and slightly less dense regions that gravity could then latch onto over billions of years to form all the structures we see. Stars, galaxies, galaxy clusters.
So inflation provides the origin story for cosmic structure too. That's amazing.
It really is. It ties everything together quite neatly. As Alan Guth himself famously put it, reflecting on how inflation could generate the energy and matter of the universe from almost nothing, it is said that there is no such thing as a free lunch, but the universe is the ultimate free lunch.
The universe is the ultimate free lunch. That's a fantastic quote. But, for some people, that might sound almost too simple or maybe too convenient for how everything began. Such a powerful mechanism solving all these problems at once. Were there, counter-arguments or maybe alternative inflation models proposed that offered a different perspective?
That's a very fair point. And yes, absolutely. Since Guth's original proposal, there have been many, many variations and refinements to the basic inflationary model. Scientists are constantly working to make it more robust, connect it better to fundamental particle physics, and figure out ways to test its predictions more precisely.
So what are the main areas of debate or refinement?
Well, key questions include, What exactly caused inflation? What was the physical mechanism driving this exponential expansion? The leading idea involves a hypothetical quantum field, often called the inflaton field, that permeated the early universe.
An inflaton field. Okay.
This field would have had a high energy density, creating a kind of repulsive gravity effect that drove the universe to expand exponentially. Then, how long did inflation last? And critically, how did it end? Obviously, the universe isn't inflating exponentially today, so there must have been a mechanism to stop it.
How did it stop?
The idea is that as the universe expanded and cooled, this inflaton field would have decayed or rolled down an energy potential landscape, like a ball rolling down a hill. This would convert its energy into the particles and radiation we see today, effectively reheating the universe and transitioning it into the standard hot Big Bang phase. This process might also be linked to how the fundamental forces of nature separated. Yeah, the idea in grand unified theories is that at extremely high energies, forces like electromagnetism and the nuclear forces were unified into a single force. As the universe cooled after inflation, this symmetry would have broken, allowing the forces to differentiate into the distinct forces we know today. This symmetry breaking could be the very mechanism that ended inflation.
So the end of inflation is tied to the forces becoming distinct.
That's a leading possibility, yeah. And what's crucial about this whole picture is that it suggests the laws of science, the laws of physics, can hold everywhere, even potentially right back to the very beginning of time, or whatever quantum state preceded it. It implies we might not need singularities, those points where physics breaks down, to describe the universe's origin. Quantum theory might be enough.
But what happens right at the very first moment, even before inflation presumably kicked in, when gravity would have been super strong and all our classical theories like general relativity just completely break down, that's where the concept of time itself gets really, really blurry, doesn't it?
It absolutely does. This is the deepest question, the ultimate frontier where classical theory simply cannot provide an answer. To truly understand the very earliest stages, perhaps even the creation event itself, we need a complete quantum theory of gravity. This is where physics gets truly abstract and fascinating, pushing well beyond our everyday intuition about space and time.